All right, so how you guys doing today? Good. I'm good. Perfect. Thank you. All right, so let's move on to the next topic in chapter 16 now. Yeah. So then we talked about the electrophilic aromatic substitution. So basically what we've been talking about was this one. If you have some aromatic ring, when you have a really good electrophile, looks like this, and you're going to have substitutions, eventually you're going to get this one. So we talked about why it has to be substitutions and then how it works basically, but because of the stability of the aromatic ring, like a benzene, we'll do this type of special reaction. We call this electrophilic aromatic substitution over here. Okay? So we talked about the halogenation, the nitrations, and some possible sulfonations and everything. So we started with the halogenation on Monday. Okay? So let's try to do some quick review, and I'll move on to the next type of the electrophilic aromatic substitution. So the one we talked last time was about this one. You have so the first one was the halogenation. So we have a toluene. When we try to fluorination, we use one of the fluorine, which is the quite reactive. So we actually find a good way to make it happen was using this one. So we actually gonna use this compounds. So we actually going to make some products with halogenation of the aromatic reactants over here. So you actually going to have on alter and then para substitution of the hydrogen position here. So this will be two possible scenarios. So as you remember from the nomenclature we did before, this is orgo fluorotoluene, and then para fluorotoluene too. Okay? So this is fluorination here. So this was kind of special case because of the fluorine is very small and reactive, but this is an exceptional case. But most of the time, we use the chlorine and bromine. We're gonna use some iron chloride, iron-free chloride, iron-free bromide. So you can use those two catalysts to make it happen. So whenever you have benzene over here, okay? And then those two will behave like here. Okay? So so it goes to here, here, and then they become iron Cl4 minus iron 4 minus. And when they go to there, they become that's over here. So this will become your good electrophile that we saw before in the basic form of the electrophilic aromatic substitution. So this is why it attacks this one and this one. So whenever they do, this is gone now, right? Cl. Okay, oh, this is gone too. And then you have this one goes to what? So you have a ion 4 minus, ion 4 minus here. Okay, and then you're going to have this one. This one attacks goes to stack goes to. Okay, so when it happens to this one, they're going to back in the original aromatic ring structure. So HCl with their original catalyst, iron 3 chloride, iron 3 chloride. So this is just a review. You can also watch this again on Monday lecture, but this is a halogenation, simply just using one of the substitution from the aromatic ring. Okay. So the other one was iodination, was the almost similar. So you have this one over here, and then we're gonna use one with the copper 2 chloride. So what happens to this one is you have iodine diatomic molecule with the copper 2 cations, and then they become 2 iodine cation, and 2 confluous ions over here. Okay. So then now you have a really good electrophile to tap on from this here. So same from here is pretty much the same. And over here. Now it's left here. But this is picked up by the base. So attack. So there goes to original aromatic ring form with iodination. This is pretty much what we did last time. Okay, so the next one we briefly talked on Monday was nitration. So nitration is to be done by nitric acid and the proton donor, which is maybe sulfuric acid over here. So when you look at this one over here, okay, if you look at this one over here, you have a nitrogen center atom over here with the 1 double bond on the 1 oxygen here, and 2 oxygen to the single bond. So this is a positive charge. In total, -1 charge. But because this is acidic form, so this is why it can be a strong acid. You can easily donate the proton over here. That makes the nitric acid quite strong. So you can be always donating this proton here to be in nitric form. So if that is the case, what happened to this one is you're going to have a lot of numbers of protons will be available on the environments over there. So what happens to this one here is actually this will become catch one of the hydrogen cation protons, and they actually going to have water groups on here, which is if you guys remember this from the chapter 11, last chapter in number 1, this water is really good leaving groups. Okay. So meaning they're actually going to leave here. So they take this here, so they become water. water goes taking this pair of electron on here and become water. Okay? So to make that go, and there's a 3 lone pair on this negative charge oxygen goes to here, so they can make the double bond over here. Okay? So this is gone now, and now there's a double bond. Okay. So this will become, do you see? So this part become nitronium ion. This. Okay. Now it's a 2 double bond over here, and it's positively charged. And then once again, this is your electrified now. Okay. So we're pretty much doing the same thing over and over and over. So then they're going to catch that one over there. Okay. Because it's a positive charge, right? So it's really good nucleophilic, electrophilic type of interaction there. So then you're actually going to have so when it moves to over here. So there was to this form, okay? And then later, this hydrogen will be catched by the water. Do you guys remember the water was there once it break apart from the nitric acid with the numbers of the protonation? So this will grab this one, and this goes to the bond in here, goes to make double bond over there. Okay? So the outcome is here. Okay, when this becomes hydronium cation, because the water catches the here, which is the H plus, because there's a lone pair. The electrons in the bond shared to the carbon and hydrogen all goes to the making a double bond. So this is sorry, I forgot about putting the positive charge will be gone. So positive will be gone, and then this will be double bond over here, and then this is the product from the nitrate. So this is I briefly mentioned. So I did it again today because I only spent a few time. So this is nitration. Do you guys? I also briefly mentioned about this one too. But do you guys know why it has to be in this form? Because it's because of the double bond. Because of the pi bonds in the double bond, it is unable to. Think about it. If you have a plus charge in here and negative charge here, it's really, really unstable, right? So what wouldn't they do this one? My question is, why wouldn't they do this one? They just move there, right? But they just don't do it that way, okay? Because of the, in this way, nitrogen has 1 single bond and 2 double bonds in this case, which is electrostatic wise much more stable, but the problem is they can do it by its structure. So if you think about the sigma bond and the pi bonds, right? Here, it is only possible when it's kind of linear, so they can be elongated, conjugated into another. But if it's in the angle, you have to do it this way. Right? So this region will be overlapped by POV, or involving the pi bonds. So this is actually unstable. This is actually more stable than one. I mean, the plus negative charge will make some instability, but still better than this one. So that's why we having this one. Kind of makes sense. So basically, the only thing you have to know is the nitration process. If I give you this, what's the product? You just need to choose this one. That's it. Okay. This is the only thing you need to know for this. Kind of makes sense. Okay. So just But if you have any questions, just let me know. I can always help you with the detailed mechanism. For the exam, the mechanism is too much to memorize for each chapter. So if you just know what might be the product out of these two, the reactants or the catalyst. So can I move on? Yes? Okay. So the other one is sulfonation. So sulfonation, we're gonna use the sulfur trioxide, okay, with the this one. So okay. So now you guys wonder, wait a minute, I just mentioned about the double bonds can be in the like a bond angle, like unless it's linear. This is kind of a special because if you look at the sulfur, it's bigger than nitrogen. Do you see it? So that means this one has a bit of a more ability to do some little bit of angle between two double bond is okay. So whenever you have so think about it. Whenever you have a sort of a big like a big atoms, so you means you have a bigger space to store the electrons. So if you have a bigger space to arrange the electrons in the common ground to make a double bond or a single bond, it's easier for them to make those two in an angle. Is easier for them than the one that is smaller, because they have a much bigger space. They can be somewhat flexible on this use of that limited space. Kind of makes sense, right? Kind of. Okay. So anyway, so if that is the case, this is what you can do. So you're gonna have a lot of protons here too from the sulfuric acid here. So don't need a lot of proton. So they can have they can be protonated over here, which meaning they're going to grab this one from over here. So they're gonna grab over there, and then they can be also is good. Once again, this is our electrophile here, and then you're gonna have my drawing is really weird. Okay. So you can have this one attack, right? Because it's now is a really positive charge in the electrophilic here. So what happens to this one? Okay, I'll just do it in this way. But so once it's gone, okay, but it moves. Okay, so now this is a positive charge because that one is gone by making bond to separate. It goes to here. Okay? So then that gives us and then this one will be picked up by some base, or you can say some minus. Okay, so then it goes to there. So then you're going to have an original form of the aromatic ring on this side. Okay, so carbocation will be gone too. You have a sulfur here. Okay. Yeah, because the 1, 2, 3, 4. Yeah. So this is a kind of weird form, but this is pretty much it's very similar to what we saw from the nitrations. So only difference is they have a more ability to arrange the two double bonds in the first beginning because of this larger atoms than nitrogen. But from there, basically what happens is when they become really nice, positively charged, the electrophile, they can be attacked by one of the pi electrons in the aromatic ring. And then once they have a carbocation with the bond, once they bond to that sulfur, they will get by the base. So they can be in the original form in the aromatic ring, which is more stable anyway. So that makes this one. So once again, same thing for this one. Whenever I give you the questions on the exam, I'll just give you this, okay, right? And then whenever I do this one, only thing you have to know is pick this one. This way is the answer, okay? So you don't have to know for the full mechanism. I think I understand it's a lot of things to do for the exam. But whenever I do this, make sure you guys choose this one as your correct answer, okay? That is the subordination we have in the one of the electrophilic aromatic substitution, okay? Type of a process. Okay? Can I move on? It's good. Okay. All right, that's good. All right, okay, so we're now done up to the halogenation, nitration, and sulfonation. The next step was, let me see. Oh, alkylation. So the alkylation, whenever you have a sort of a aromatic ring structure or aromatic compounds over here, and you have some type of alkyl halide. Okay, and then you can actually put this in this structure. Okay, this is what it does. Okay, so let me give you one example over here. This is our catalyst. Okay. So what happens to this one is this is pretty much the same, that it goes to here and here. Okay. So this is what we already saw before numerous times in other type of reactions, but this is very similar. So only difference here is they makes the electrophile. In this case, it will be carbocation compounds. So if this one happens, obviously you have aluminum Cl4 negative. Okay, this is added to there. But this will become, this part here will become, this carbon will be carbocation, right? So this is your electrophile. So this is pretty much the same now. You just need to have grab this one over here. So they will bond to this, okay? And now your double bond is gone. And you have a carbocation again here, because once it's double bond, this carbon bond to that other carbocation. But this is only 3, 1, 2, and there's an implied hydrogen here, but only 3, so the carbocation. So this will be reduced by this one, because it's negatively charged. You can grab the proton or hydrogen, and then you go over there. So it's pretty much the same, right? So you have done this, then this will be gone. So there's a pair of electron were in the bond, single bond to the hydrogen, goes to double bond over here, and hydrogen pick up by one of the chlorine that become chloric acid. Okay. So and then this one go back to its original form, which is the definition of the catalyst, which is aluminum chloride. Okay. This is alkylation. So alkylation simply means literally you alkylating the compounds by using some type of a catalyst that makes the really good electrophile that can be easily attacked by one of the pi electrons in your aromatic ring, aromatic compounds. Once that happens, they can be always picked up by later by something that kind of behave like a base that pick up again, and that becomes to double bond again, eliminating that carbocation position here. So it's now a very stable product, which is better thermodynamically. Okay. So it's very similar, right? That we saw many times in other type of interaction here. Okay. But the alkylation has sort of the several limitation here. So alkylation has about 4 limitations. The first one is whenever we're talking of the alkyl halide, you cannot use aryl halide, which means aromatic ring groups. So for example, like this one, this is like a aryl halide, one of the example, or phenylic halide, meaning like you have a double bond here and there's chlorine. Okay? So those type of thing. So these aryl or phenylic halide cannot be used for this alkylation. This is the what we call Friedel-Crafts reactions. This type of alkylation, we cannot use the aryl or phenylic halide. So it will not happen. If you try to do the alkylation with those two, will not happen. So this is the first limitation. Okay? This is the first limitation. Okay. First. The second one, it will be affected by the substituting groups. So the second problem is the substituting group effect. Okay? Group problems, I can say, problems. So what I mean by that is the if you have aromatic compounds, which is some phenyl ring or benzene ring over there, and then you have some groups on here. Maybe you can say it's Y groups. Okay? If that Y group is the electron withdrawing groups. For example, like we saw before in the dinophyte, right? With a lot of groups with the carbonyl groups, carboxyl groups, aldehyde groups, and a lot of things. Plus all types of amine groups, like HN2, HRH, or the R3, or the all amine groups over here. So the plus, this is plus. So if that is possible, if there's amine groups or any type of the electron withdrawing groups on your aromatic compounds, you cannot do. It hardly can be done with the Friedel-Crafts alkylation here. So this is the second limitation. Okay. This is quite important because probably on Friday we're gonna talk this in very detail about this possible scenario you can do with the activating, deactivating group with the ortho meta para position on the substitution reactions. But we'll get to that on Friday. But this is another limitation we can find in the Friedel-Crafts alkylation. Okay. Okay. So the third problem is the polyalkylation problems. So that means it is hard to stop when it's done the single substitution. So whenever you do, you try to do this, right? And then you have a tension here when it's breaking apart, negative charge. So then they will tap to here, right? So they can be alkylated in this way. So this is one time done. So this is what? This is the single substitution. But sometimes they do one more time in a row. So this one pick up again, another carbocation attached to that one, and then makes the substitution. I'm sorry, I also didn't explain, but this one, that's pick up by hydrogen, goes in double bond, right? So then this will be what we call polyalkylations, because you do the alkylation more than once. So sometimes you have, whenever you do this, you're going to have this one for sure, but you have a lot of this one as well. So this is a major product, and this is a minor. So mean if you want to do only single substitution, it's really hard to do with this one sometimes. This is the third problem when you think about the calculation, calculating your arithmetic or compounds. Okay. The last problem was oh yeah. So this is similar to this one. Okay. Okay. So can you guys probably by now, whenever you do this with this catalyst, goes there positive charge, right? So you have this one, okay? You see this now, right? ACl4 minus, okay? So this will be attacked here, okay? Attack here, and then once that attack here, it will become and then this will be positive charge, right? And this hydrogen will be picked up by this one. It goes to there, so okay. So this is expected products, as you can see, right? You see that, right? This is expected products by following what we have learned from other type of the substitution reaction from aromatic compound. But you do have this one too, but you also have this too, okay? So this will become more major here. And so technically speaking, you need to have the carbocation in this position when this chlorine took up by the catalyst. So this is the one, the position, the carbon that has to be attacked by one of the pi electrons in the aromatic compound. But you get this one, but a lot more of this one because of this. So whenever you have so when it happens here like this, okay, you have this one right now. When it happens, this one is, as you can see, this is a carbocation with only one primary positions, because they're only binding to one carbon here with just two other hydrogens here. You see that, right? So what happens to this one is they actually move to here so they do it by here. So I'll draw this, okay, over here, right? Okay, this is what you see. This is what it actually looks like, right? And then if you actually have a sip of the hydrogen with hydride, okay, goes to here, then what happens to this one is the more stable cation. Because now in this position it has two carbons, it's a secondary. Carbocation. So obviously, when it's surrounded by more numbers of carbons, more higher degree in the carbocation will be more stable. So whenever you have this part after the halogen took by the catalyst, it goes to this position by shifting your hydride here. They do that because they want to make the more stable carbocation position in the compounds. Okay. This is related to what we learned in over 1 when we talked about the stability of a carbocation. Okay. Do you guys remember this actually from the carbocation? So, but it kind of makes sense now, right? Why they do the shifting on here? So that's why they attack here, not here. I mean, they do here, but just very small chance, but more in here because that is more stable carbocation. That's what they this compound want to do after they lose the halogen groups there. Okay, so then you're going to have. So that is why whenever you have aromatic compounds with this one, you can also think about this one, but also this one, which will be more stable. Okay, so then minor. Okay, so the let's change this one to a bit more tricky one. Okay, so if that is this one, oh no, okay, this one, okay. So I'll tell you the answer already. Okay. So what happens to this one? So technically, if you think about it, this will be taken by here, then your carbocation position will be here, right? So then it has to be. I mean, we all do, you know, this is what it looks like. We should look like, right? But what it actually look like is this one. This one. Okay, so this is a bit more tricky because the same reason. So this won't be very likely to happen because of this is a very primary. It's only one carbon next to it, so it will be not so stable carbocation anymore. But it can move to here. That would be great. But the problem is this carbon does not have hydrogen to make a shift, right? So then the funny thing that happens is they move to, so this, you see that, right? So this is the 40, I'm not gonna put all the hydrogen here, but it goes to there. So what happens to this one is now it becomes I know it's weird. They're actually moving not just hydrogen, but the carbon itself. So this is a carbon, this is a kind of method type of carbocation rearrangement. That's what we call. But indeed, it will make very stable carbocation for sure in here, which is very tertiary carbocation, which is very the tertiary. No, wait a second. Oh no, sorry, not tertiary. Here, which is more stable here. Okay, so that's why this will attack this one, not this one, okay? This one. That's why we saw this one, okay? It's kind of weird, isn't it? I swear. There's a lot of things happen in the organic chemical reactions. But mainly it's because of the carbocation stability. Once they lose the halogen on the alkyl halide here, they want to move that carbocation position to be in a more stable form they can do, which they do it, then they pick up that stable, most possible stable form of the carbocation, so they can be in this way. Okay, so this is the last problem of the Friedel-Crafts alkylation, which you can't always the product you want to have because of the this type of shift on your carbocation compound. Kind of makes sense. Does it make sense? You good? Okay. So I'll probably do it again maybe next time, especially before the exam for sure. But it's just mainly because of the stability of the carbocation. So once again, this might be a bit tricky, but you don't have to know about how they shift the carbons and hydride, but just know whether the most stable carbocation form you can do with the alkyl groups on that alkyl halide. You may see that as your best choice because of this. Okay. So on the exam, you just need to know this one. There might be some tricky question like that one, but that you need to think about when you try to solve the problem like that. Okay. It's a bit tricky. All right, see. Let me actually give you one. Okay, so maybe. All right, let's do one problem together then. Okay, so I'll give you about. Oh, what? It's already 40 minutes. Okay, let's do this as extra credit. Okay, so I'll stop here.
So the